The title of my talk is What is pi and what it is not. It is much easier to answer the second part of the title. So let me tell you. Statement. Fact. Pi is not a number. If you get this, you got everything important from this talk. So you're welcome to live now. That's the most important message. Pi is not a number.
Doron, I know this is an alternative version.
And I was thinking I was so subversive, so innovative, so not a dissident when I say pi is not a number. Then it turned out we have a visiting day tomorrow for visiting graduate students. And one of the prospective PhD students who is considering coming to Rutgers is Mr. Robert Dougherty Bliss. So being in the age in 2019, whenever you told that you're supposed to meet so-and-so, the first thing you do is look them up in Google and make sure if you did anything interesting or important or maybe embarrassing. So sure enough, I looked them up, and Robert, I recommend to everybody if you just Google Robert Dougherty Bliss, or even by the title. So the title of his talk that was videotaped was 2, the number 2 does not exist. So he told me, I do believe that the number 2 exists, number 3 exists, and up to even a Googleplex. But pi is not a number. Being a mathematician, I have to prove it. Prove a contradiction. It's not a number. In 1882, somebody called Ferdinand Lindemann proved, quote unquote, that pi is a transcendental number. So it was a correct proof, but the phrasing is completely wrong. By saying pi is a transcendental number, he implies that pi is a number. It's a kind of number that is transcendental. What he should have said, pi is not an algebraic number. Only rational numbers, and if you're really broad-minded and liberal, algebraic numbers exist. I define them shortly. Anything not algebraic is not a number. And if you're really a fundamentalist, even square root of 2 is not a number. So when you say square root of 2 is irrational, it's a stupid statement. What the proof the square root of 2 is so-called irrational is a proof by contradiction the square root of 2 is not a number. So square root of 2 and pi are not numbers. What are they? I'll tell you by the second part of the topic. So what is an algebraic? What's a rational number? Rational numbers do exist. And Pythagoras had a religion that every number is divine. Every number is God. They worshipped numbers. And they were even willing to take fractions. So this exists, so no offense to Robert, 2 does exist. And this exists, even this exists. Ratios of 2 integers, that's a rational number. They do exist. But what does it mean? Calling it x, you can cross multiply and have certain x, 1 plus 3 equals 0. It satisfies an equation of degree 1. So if you are more broad-minded and more liberal, you can define, include as existing this. But now square root of 2 does exist, but not as a number. It exists as a symbol, and also later on as an algorithm. I tell about it. Or as an equivalence class of algorithm. I'll talk about it later in the context of pi. But right now, this is a finite object. I can write it down on the computer. So if I define x as the positive number that satisfies the equation, then it's okay. and I can manipulate it, and since this is the defining property, I can compute with this. So as long as you can compute with it, this is fine. So from now on, square root of 2 exists. So algebraic numbers are only a slight extension of rational. So that's an example of an algebraic number. But now it's degree 2. This is also, and you can write it down with integer coefficients. So it's okay, that exists. Of course, there are 5 of them, but all exist in mind. I'm still willing to accept it. So what Lindemann proved was that pi does not exist as a number. There is no such equation with integer coefficients. So that this is true. So he gave a proof by contradiction. Now there's a famous quotation by Kronecker. Kronecker is a Zeilberger analog of the 19th century. He famously said, God invented the positive integers. Everything else is artificial humankind. And he once told Lindemann, what use is this beautiful, deep result about pi, since it doesn't exist? So what he did is something not very interesting. So he was wrong. But he just misinterpreted it. What Lindemann proved was that pi does not exist. And you cannot say, most people believe that pi is a number. It's a ratio of the circumference to the radius. So the conventional wisdom for a long time that pi does exist as a number, as the so-called real numbers. But this is nonsense. Real numbers do not exist. So let me tell you another common misconception. Wrong. Pi equals 3.14159265535. True or false? What do you think? David, is it true or false? This statement.
You haven't listed enough terms for me to say further.
I'm going to go with meaningless.
Okay, yeah. It's not even wrong. It's meaningless. Because this dot 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 implicitly assumes that it can go forever. Just out of practical reasons, because we humans are finite, it assumes it can go forever. This is a meaningless statement. What is meaningful is the following statement. Pi is between 3 and 4. Pi. So you have intervals. So, yeah. And so on. So these are meaningful statements. So the only meaningful statements concerning so-called real numbers are statements that x is between a and b. But these numbers are rational numbers. They're the only numbers that truly exist. So how to define pi? Pi is not a number, but pi is something else. So now let's go to the second part of the title. What is pi? So before that, let me remind you analogously. What is a number? I do believe in numbers, integers. But what are they? We take it for granted. For us, the number 2 is very, very concrete. But if you think about it from a deep point of view, it's an extreme, extreme abstraction. It's really very, 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 very deep. In the old days, the cave women did not know what 2 was. They didn't have the conception of 2. They only had concrete objects. 2 bears, 2 children, and so on. Then much, much later, a great logician called Frege. And it was popularized by Bernard Russell. He proved the following for a cardinal, so-called cardinal number. So 2, definition. 2 is an equivalence class. Of all sets with two elements. Now, you might say, some definition. Isn't it circular? You define 2 in terms of 2. So, here's the big quotes. You look at the equivalence relation between finite sets. 1-to-1 correspondence. And then you have Joel and Matthew, Matthew and David and Neil. So you have lots of sets. In my philosophy, still a finite number of them, but lots of them. And the equivalent, if you can do 1-to-1 correspondence and take the equivalence class, so it's just an equivalence class process. So my analogous definition of pi is or any number is an equivalence class of algorithms. Algorithm is something concrete. Algorithm is something that I can code, that I can write. It's something finite. Another pet peeve, speaking of algorithm, the father of computer science, Alan Turing, famously proved that the halting problem is undecidable. This is nonsense in my philosophy. What he did prove is that the halting problem is meaningless. He proved a contradiction, so he tacitly assumes that you can run the program forever. So this problem is not well posed. So this is, by the algorithm, the halting problem is a stupid problem. By the notion of algorithms with input and output is a good object. So here are some definitions. Yeah, so you have an algorithm, and it's an algorithm to generate 2 sequences of rational numbers. And for every input n, there is output a and bn. And if you have the property that if you have n is bigger than m, so it is basically mimicking the definition of convergence, a delicate cut, but in a new light. Then if the interval gets smaller and smaller and smaller, so for any epsilon you have an input, then you can generate this. So it's an equivalence class of outputs of algorithms. So there's not just one pi. There are lots and lots and lots of pi's. And now we describe some of my favorite definitions of different definitions of pi, and they all have something in common. Each interval can be inserted in the other of the interval. So it's an equivalence relation of pi's, of sequences, of pairs of integers. So being a finitist, I don't like this notation, because this assumes you can go forever. For example, this statement is nonsense because of this. But you can make sense out of it, so let's erase this. And you can define it, perhaps as usual, by the epsilon, blah, blah. So it's an algorithm, and you can do it. So here are some of my favorite definitions of pi. And for the sake of simplicity, I just use limit instead of the upper bound and lower bound. You can make it into 2 intervals, but you can easily. Look at the number of lattice points. X, y. So that x is between minus n and n. Y is between minus n and n. divide by n squared, and take the limit as n. This is pi 1. Another definition of pi 2.
Doron, for that first one, do you need something like x squared plus y squared?
Oh yeah, thank you, thank you. I will be 1. Thank you. Yeah. Thank you. I will have the answer will be 1. So it's this means of 1. Thank you. So that's basically, so area does exist in discrete. So this is meaningful statement. For every n, you can count lattice points and then take the limit, but in my sense of limit. Another pi 2 is the following. The limit as n goes to, sorry, limit of n, I have to click for the limits for the n. This is something completely combinatorial. This is essentially the probability. If you toss a coin 2n times, and you have exactly n heads, let's take it reciprocal and put n. So price for price, you have the limit. So this is the area, a version of the fifth scale definition of pi, is the area of the circle, and this is the probability. Speaking of this, here is my pet peeve. One of the greatest physicists of the last century, Eugene Wigner, has a famous essay, The Unreasonable Effectiveness of Mathematics in Science. And he was raving about the amazing usefulness of mathematics that we neither understand nor deserve. And so he started with the following anecdotes. He has a friend who has population dynamic, biological, biostatistics. So he saw this function, this integral, the normal distribution, whatever. Power 2. Yeah, okay. So he saw something like this. He said, what is this symbol, pi? So he was starting a statistic paper, biostatistics. So he was a layman, so he saw, what is this? What is this pi mean? Pi is 3.145.9, etc. Is this? I said, but this is something to do with the area of a circle. It doesn't do with statistics. How could it be? And he was so amazed that the same pi that showed up in statistics or probability also showed up in geometry. And I was all amazed. And I have a way of explaining this coincidence, quote unquote. It analogous to something in linguistics called Zipf's law. Some words like if and et and how are you doing and have a nice day are very, very frequent. And some of them have very obscure word. For example, I just learned from a crossword puzzle the word grog, which I didn't know before. I looked it up. Does anyone know what grog means? Yeah, you probably know. Yeah. Anyway, grog, understand intuitively. So it turns out, if you look at the frequency of a word is inversely proportional to its ranking. So common words show up a lot because they're simple. So pi and e, the reason to show up a lot because they're so simple. The definition is so simple. So let me give you something and that goes in combinatorics. The Catalan numbers. And you go to the OIS, there are many. And Richard Stanley wrote a whole book about it, how it shows up. And people think it's a miracle. But the reason it shows up so much, because it's the simplest sequence of its kind that satisfies certain things. So something analogous happens to here. So pi, one definition of pi is the Okay, sine of pi is 0. So one definition of pi with calculus is the smallest positive root of the function sine of x equals 0. But what sine of x is a solution of an extremely simple differential equation that comes up so much. It's as simple, almost as simple as you can get as far as differential equations go. And the only thing simpler, and that by E shows up even more, is this differential equation. Because we humans can only do simple things, it makes sense that only simple things will show up. So this is a meta explanation why pi shows up. So, but let me now tell you some more interesting ways to compute pi, approximations to pi. So it's really an algorithm. So since there are so many algorithms, the fastest you converge, the better. So here is one that I really like, and I did it in my class today. And also it's amazing way how it shows up in combinatorics naturally. We all know about permutations. The n factorial permutation altogether. Now, let's look at this permutation. Let's look at random permutation. It goes up, it goes up, it goes up, it goes up, then it's down. So it's up-down behavior is up, 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 down. If the increasing permutation is up, 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 up. So it's called zigzag or up-down permutation. If it's ups and downs, ups and downs, ups and downs. So let L of n is the number of up-down permutations. Something completely combinatorial, nothing to do with pi a priori. Let's count them. How many are they? So today in my class, experimental math class, we did it by brute force first. If you want to find out whether this problem has been done before, what is how you do it today? In the beginning, you don't try to be too clever. To get the first 6 or 7 or 8 terms, you can do it completely by brute force. Let's do it for n equals 2. 1, 2, 2, 1. Up, down, you don't up, down. N equals 3, so A of 1, of course, is 1. A of 2 is 1. So n equals 3, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Now literally, you can see do it by hand, get it up and down. This is okay, right? This is done up and down. And this is, no? So how many 2? So I have these 2. So the computer can easily do it up to n equals 8. In a second, we got the sequence. I don't remember it by heart. Blah, blah, blah. So in class today, we copied and pasted it. We went to the internet to the very, very amazing online encyclopedia of integer sequences that I'm very fortunate to have Neil Sloan right here in the front row. And sure enough, we found out that we were scooped. In fact, it goes back to Euler. So Euler did not care about combinatorics, at least not in this case. But it found a different interpretation. In fact, it's a little bit where it's stalled. It stalled my point. So it was a mixed passing going to the IS. So I was trying to motivate the generating function. But if you go to IS, you already find out. So it has secant of x, but 10 of x. So that's a so-called exponential generating function. So that's how you find out that you have been scooped. And then if you look at the other information, that one of the interpretations is the number of up-down permutations. So, anyway, suppose you didn't know that. Suppose you didn't have OAS. So suppose you do it completely from scratch. So this will only get you so far doing it by brute force. Suppose you want to compute the first 1,000 terms of this sequence. 1,000 factorial is too big a number even for the computer. So you have to be a little bit clever. You do a recurrence, or the fancy name is dynamical programming. You analyze, you take the anatomy of a typical up-down permutation, and you try to find an efficient algorithm to compute them. It's a sequence of integers. So you look at a typical permutation of length n. N has to be somewhere. Remember when we proved that the number of permutations is n factorial? We say n, the loudest, so it has length n. The loudest entry n is either the first place, the second place, the last n possibilities. If you kick it out, you have n minus 1 factorial. So, let's be the location k. But unlike a general permutation, for which n can reside everywhere, not for up-down. For example, n cannot be in the first place, because if in the first place, it's a down right away. So, it cannot be in the first place. Similarly, it could be in the second place. It cannot be in the third place, for the same reason, because at the end it is. So, it's obvious that the location of n has to be even. That's the only way. Now, if you look what's before and what's after, you have a brand new permutation of length 2k minus 1 and of length n minus 2k. And they are up down on their own right, yet inherited. So we use so-called dynamical programming or recurrence. A of n, if you sum over all the conceivable k from 1 to n, so it's 2k. So we have a of 2k minus 1 and a of n minus 2k. But this is not correct as it stands. This is not a permutation of 1 to the left. That's a permutation of an arbitrary set of integers. So you have to make a choice who will reside on the left and who will reside on the right. And we have 2n minus 1, choose 2k minus 1. So this is a quick way to generate the first 1,000 terms or whatever in Maple. This takes one line Maple code. And you do option remember because Maple remembers it, so you want repeat permutation, and you get it right away. And you did it in class, so you take the sequence, and you look at the ratios, and you have a sequence of rational numbers that do exist. They get closer and closer and closer to so-called pi. And here goes. It's the limit, so this is pi 3. And that's if you go from. The limit is n. 2 times n, a of n minus 1 over a of n. So this is the sequence of rational numbers that do exist. They converge, but they can always converge, quote unquote, meaning you can open pi to pi. And this is much faster. So this is something that Archimedes could have done. Archimedes worked so hard to do upper bound, lower bound for the circle. If you want to approximation of pi, could have done in equal compute this, and the first 10 term, Archimedes could have easily done it, even without a decimal system, he could have done it, I'm sure. And so this part, so 20 times a of 9 over a of 10 is already better than what Archimedes did this. So this is how you can, and the convergence is very, very fast. So that's another way how pi comes naturally in combinatorics. it has nothing to do with this. So speaking, but this is not as fast as some other ways. Ramanujan had an amazingly fast series to compute pi. And computer, a real wizard, both computer and mathematical, a Spanish, called Jesus Gilera, who has even better one. So here is one of the Ramanujan one, here's one of his. So he even beat Ramanujan. Here. Okay, here's Ramanujan. Square root of 2 over 4 pi. So you have to. So this is very, very efficient. 1/2. So let me define. A sub n is a rising factorial. A times a plus 1 times a plus n minus 1. So this is famous Ramanujan. Ramanujan was a genius, and he came up with this very, very fast series that gives you pi to many, many digits. And then you have this 2, 6, 3, 9, 0, n plus 1, 1, 0, 3. And now comes what makes it so fast. Divide by 99 to the power 4n plus 2. So this is Ramanujan's. And it gives you 5 digits for every new term. It's very, very, very high. But Jesus or Jesus Gilera came up with something even better. So, once again, for my philosophy, it's a sequence of rational numbers, except for this. So, if you want to really be rigorous, you have to square both sides, and then you get it. But then you have pi squared, never mind, suppose. So here, you just take partial sums. So you have a sequence of 6, and this is another algorithm for pi. So and this is much better than even this one. Also maybe not this, yeah, and again. And Jesus Gilera is something even faster. Yeah, but I won't put it. So this is, and here's even a better way of computing sequences of rational numbers that do exist that converge to pi very fast. When you were in 5th grade, your teacher probably told you that pi equals 22 over 7. Then later on, you were told that it's not exactly right. But it's close. And what you have, yeah. So it's algebra 22, the difference. So this is an upper bound thing. So it's even to the integral that maybe you can do very fast. X to the power 4. 1 minus x to the power 4. So you can see that this is fairly small because the maximum of this is at the middle, and this is even less. So you can easily estimate and find that it's not. It's pretty good approximation. But why stop here? You can define a sequence of numbers, quote unquote, k of n. And equals for n. And this gets much, much smaller. And it's very easy to see the format of each of these. So you take, remember from Hack 2? you do partial fractions. You take the remainder, so this gives you something with pi, and the rest is a polynomial. So it's always the format, a sub n minus b sub n times pi, for some rational numbers. And this is extremely small as n gets. So this is almost 0. So you get a sequence of very good approximations for pi using this. So this maybe you can do it's up to n equals 100, but once you get to n equals 1,000 or n equals 10,000, it gets to be very slow. Luckily, there's a quicker way of doing it. And this gives yet another definition of this sequence. You go to the method package, and you use a command called AZD, the discrete Almquist Zeilberger algorithm. By the way, Gerald Almquist, my collaborator, was an amazing mathematician. Unfortunately, he passed away a few months ago. And in the first talk in April, Zeilberger, I mentioned, will give a memorial talk in his memory by this matter. Anyway, so if you do AZD into this, blah blah blah, you get a very simple, not so simple to humans, relationship, a recurrence, a second order recurrence. Some polynomials, which is too much to write now, some other polynomials, specific polynomials, I'm too lazy to write down. But this second order recurrence, you can compute 10,000 terms of this very fast. So you get the an minus bn, and this is a condition, of course. This condition, k of 0 is pi over 4. But again, my pi is it's symbolic pi. It's not u pi. And k1 is 22 over 7 minus pi. So once these two initial conditions, you can crank out, and you don't need, you can have 10,000, and you get, it's very, very close. Tiny, tiny, tiny. So you pretend it's 0, you get very good approximation. So that is another algorithm to generate pi. So pi is really an equivalence class of many, many algorithms. Some are faster than others. And here is another amazing thing. One of the slowest algorithms, however, so this is very fast. This is also very fast. But it's not fun to have fast. How about slow? So does anybody know one of the slowest algorithms to compute time?
Is that the one minus the third plus?
Very good! This is due to Leibniz or Gregory or whatever. Pi equals, so pi, in my sense, is a algorithm. 1 minus 1/3 minus 1/5 minus 1/7. Yeah, so once again, you have, this is even, and when n is 1, yeah. Okay, so define a sequence of rational numbers. And if you go far enough, you get good, better and better approximation. If you remember from calculus 2, the alternating sign test, which I call the Pipok test, the error is the last one. But to compute 6 digits, you need to go up to n equals 1,000,000 roughly. 10 digits, you have to go up to 10 to the power 10. So it's very, very inefficient. But about 25 years ago, an undergrad at the University of Waterloo, I think, by the name of Artie knows, just for fun, did the following on the computer. He summed it, he ran to the computer, it went out up to 999999999. And he did enough digits, and lo and behold, he got the following answer. Remember, it's a very bad algorithm with very bad error. So what did he get? And here's what he got. So when he did on Maple, 3.14159. So of course it's accurate up to here because he went up to 1,000,000 terms. So 1,000,000 terms, you get 6 digits. But then something went wrong, 0. But then he got 6, 5, 3, 5, 8, 9, 2. So for the magic thing, most of them were right. With a few exceptions, this super slow, inefficient algorithm, if you truncate it in the right place, in fact, a power of 10 minus 1, then you get most of the digits with a few exceptions. Yeah, so then it continues. You could try a bit. 4, 6, 2, 6, 4, 3, 3, 8, 3. And the next one is wrong. So only these are wrong. The right version here is 2. The correct digit here is... So, yes, sir. So with a few exceptions, it is how to explain this phenomenon.
What is the instead of 6? What should be there?
Oh. Yeah, 4, 6, yeah. 4, 6, 2, 6. Yeah. Yeah, blah, blah, blah. And instead of 6, so this is correct. It's correct. Instead of the 6 is 7, yeah. So, yeah, so it's almost correct. Amazing. So this was computer-generated curiosity. That this super notoriously slow series, if you truncate it in the right place, namely less a power of 10, in this case 10 to the power 6 minus 1, you get many, most of it is only few typos, but otherwise. So they were computer-generated discovery. But how to explain it? How to explain this miracle? Then 3 brilliant mathematicians. One of them, unfortunately, died 2 years ago, Jonathan Bowen, who's a pioneer in pi studies. He and his brother maybe lived for a long time. Peter Bowen wrote many books on pi. And together with a colleague in that house here some time ago, a counter they wrote a famous paper explaining this. The paper was very insightful, and then my frenemy, George Aldous. So in 1993, I wrote a controversial quote paper about the future of mathematics, how proofs are going to be passé, and computers will take over, and so much can be done by computers. And George Aldous, who is my frenemy, is a good friend, but also philosophically we disagree, in particular in many things. Don't tell anybody, but I have the George for you because he voted for Trump. Don't tell anybody. Not because he likes Trump so much, but he even hates Hillary even more. Anyway, so he's an arch-conservative, both politically and mathematically. So he wrote a rejoinder a year later. You can look it up on the internet. The death of proof, you cannot be kidding. And then an example of why you still need human insight to see what's going on, he gave this paper by Bowen, and Dusser explaining. You say, computers are very good for discovering conjecture, but to explain them, to get insight, to then Gerd Anquist wrote me email a few days later and told me how he redid this article by Bowen, and Dusser in one maple line. So it's one command. You go to maple and you do asymp for asymptotic, and then you enter the sum in Nepalese. So you do asymptotic expansion, and Maple automatically got what they did, this human insight, in 20 pages, or maybe 10 pages, I don't remember, in one line. And this explains it, this explanation. So this is a numerical algorithm, that is a symbolic algorithm, but it's still an algorithm. So, so I was very amused that computers can not only do numerics, they can also complain things. So this is...
Did you get the Euler numbers?
Yeah, right, the Euler numbers were, right, exactly, yeah.
Did the computer recognize them?
It may have, but anyway, you can get as many terms as you need. So this explains why. So yeah, so as a very series. So when n is the power of 10, then most of them, it's a very sparse calculation. It starts at -2/n. Yeah, the Euler numbers. Yeah, the computer knows about Euler numbers. I'm sure you can teach it, but that's not relevant. It's just cultural. For any you can continue it. And so you know here, if any, since we're working in the decimal system, of course, an artifact of our biology that we have 10 fingers. So, but you can do the same thing in any other ways and get this amazing thing. That this very, very slow series gives you this. So let me conclude with some history, very ancient history. Pi is already in the Bible. And people who look down on ancient wisdom believe that the Bible says that pi equals 3. Because in the book of Kings, King Solomon built a circular thing, and it says it's 10 cubits, this, and it's 30 cubits around it. So the implied value is 3. These people are very stupid because God is very mysterious and God is very subtle. So if you look at the sentence in Hebrew that does it, you look at the numerical values. You have in Hebrew numerology called gematria. You have this and you have
355 over 113.
Yeah. So these are hinted, and they know, you got all the first term. So God knew it's an algorithm, and God knew you can go forever, it only has this and this. So it's implied in this. So these people who think that God is stupid, wrong, God knows about it, but sometimes he or she or it are subtle. Thank you very much. Thank you for coming. Everybody's welcome to ask me questions in private. And happy Friday.